Hello and welcome back to another episode of Quantum Mechanics. We've done something kind of bizarre in our previous classes. We've introduced the idea of a wave function, this complex function of position and time that completely describes the quantum system. Yet I haven't told you what equation governs its evolution. I haven't discussed yet what equation governs the evolution in space and time, what governs the physics of this complex wave function. And today's class will be about that equation, the so-called Schrodinger equation, which governs how this thing evolves in space and time, which captures the physics which this wave function obeys. So this is chapter 3, or more precisely the first two-thirds of chapter 3. We'll introduce the so-called Schrodinger correspondence rules. These are a particular set of ultimately ad hoc rules that will let us construct the Schrodinger equation. This will have two forms, a time-dependent and a time-independent form. Then we'll, again in an ad hoc way, state dogmatically the boundary conditions, certain conditions that the wave function must obey. Now, I've mentioned dogma and ad hocness. Ultimately, this kind of thing can only be justified. These kinds of decrees can only be justified if they correspond to experiment, right? If we could derive all this logically from first principles, we would, but we can't, so we don't. Again, emphasising the fact that the foundations of quantum physics are still a subject that's incompletely understood. So let's jump into the Schrodinger correspondence rules. These rules that will help us motivate the Schrodinger equation. Again, we don't derive the Schrodinger equation, we motivate it. So let's talk about the Schrodinger correspondence rules. So Schrodinger correspondence rules. As is so often the case, our starting point is going to be our friend the plane wave. This wave function as a function of position and time that describes a completely delocalized electron with planar wavefronts, a series of planar wavefronts filling all space, travelling in some direction given by the wave vector k. The momentum, I'll remind you of this plane wave, is proportional to the wave vector. The magnitude of the wave vector, which we call k, is inversely proportional to the wavelength, the de Broglie wavelength, the de Broglie wavelength of these electrons. These electrons also have an energy E, which is proportional to their angular frequency omega, and the constant proportionality again being h bar, which is h on 2 pi. So if we take our plane wave function, which I'll write out now, it's a complex exponential, and in here we have k dot r, but instead of k I'm going to write p on h cross. So instead of k dot r I'm going to write p on h cross dot r. So I'm just writing the plane wave a slightly different way. Then we have a minus. Instead of omega t, as in equation 10, I'm going to write E on h cross t. Instead of omega t, it's going to be E on h cross t. Now the reason I've done this is because here the wave function is going to be completely described by its momentum p and energy E. If you tell me the energy E and the momentum P of this infinitely delocalized electron, then you'll be able to construct its wave function. Just as an aside, this thing has perfectly defined momentum. The momentum is P, it's exactly P. Now you've met previously the position momentum uncertainty principle. Uncertainty momentum times uncertainty position is greater than or equal to h bar, or h bar on 2. Since this thing has precisely defined momentum, it's going to have a completely undefined position, which is why this thing is completely delocalized. It fills all space because delta p is naught, because it has precisely this momentum. Now, for the purposes of this section, we want to write our wave function in terms of momentum and energy, because this is going to allow us to motivate these so-called Schrodinger correspondence rules. And the basic idea is as follows. When we have concepts such as energy and momentum, in a classical setting, you give me a flying billiard ball, some ball bearing, and it will have a particular energy and it will have a particular momentum. The quantum mechanical picture is going to be different. We're going to think of these things as operators. Operators in the mathematical sense of the term. Yep. Operator acts on some function to give you a new function. This is an operator. For example, differentiation is an operator. You give me some function f of x, I'll differentiate it and give you a new function, f dashed of x. So operators act on functions to give new functions. And this loose definition of an operator is good enough for this course. So what we're going to do is to have this idea. This is the wave function. This gives total knowledge regarding a quantum system. If you want to ask a question such as what is energy, what is momentum, what is position, what is velocity, and so on, then the quantum mechanical perspective is that you need to, in some sense, interrogate this wave function, that using some suitable operator, more precisely a linear operator, some operator acts on this object, and from that object you extract, in a way that I'll make precise soon, you actually extract the quantity you want. So for example, if you apply the energy operator to this object, you'll extract the energy. If you apply the momentum operator to this object, you'll extract the momentum. And ultimately that statement will be made more precise. The expectation value of energy or any particular quantity will be obtained via a suitable operator acting on this. But that's a story for the next lecture. The point is, operators for this class are used to extract physical quantities such as energy or momentum, etc., from this wave function, this state of total knowledge of a quantum system. Now, the Schrodinger correspondence rules are going to tell us how to extract two particular physical quantities, namely energy and momentum, by obtaining, using the plane wave as an archetype, as a blueprint, we're going to obtain operators for energy and momentum. So the key idea is we're going to have our wave function, which will be a function of position and time. I'll suppress that now. We want to have some operator. It could be a differential operator such as d by dx or d by dt. It could be a number, 2. It could be something simple, it could be something fancy. But the key point is, when our operator acts on our wave function, we want to extract a given physical quantity. So if this is an operator corresponding to some physical quantity, let's say A, then what's going to come out is literally A comes out. This is going to be an eigenvalue. This will be a number. So you'll recognise this as an eigenvalue equation. The operator acts on the eigenfunction to give the eigenvalue times the eigenfunction back again. If that language of eigenfunctions and eigenvalues is unfamiliar to you, please revise second year linear algebra, which is a prerequisite for this course. Operator acts on function to give eigenvalue times eigenfunction, and this thing is the physical quantity that you want to extract. I should say that you can't do this in general. We'll learn how to generalise this in due course in the next class, but for now, if we want an energy operator, it's going to act on the plane wave to give the energy eigenvalue times the plane wave back again. If we want to know what the momentum operator is, have psi being a plane wave, we need to work out what operator will act on the plane wave to give momentum times the plane wave. So suppose we want energy. We want to know what operator, and I'm writing out equation 28 now, what operator acts on the wave function for a plane wave in order to give the energy as an eigenvalue times the plane wave back again. Now, if we imagine that you're Schrodinger doing this stuff for the first time, we want to extract this E out the front. And in essence, what you need to do to extract this E out the front is to differentiate with respect to time. If you differentiate with respect to time, then you will pull out a factor proportional to E, but there'll be a minus, there'll be an I, and there'll be a division by H cross. So to fix that up, we multiply by I, H cross. So when this operator acts on the wave function, and this is exercise 11, you get the energy times the wave function again. This is precisely what we want. The circle quantity on the left is the energy operator. And so this gives us, or more precisely motivates, our first Schrodinger correspondence rule, equation 30. That energy is I H cross d by dt. In very loose hand-waving terms, literally, this says if you want to work out the energy of something, differentiate with respect to time. Now, which thing has a higher energy? This or this? Yep. The key point is the more rapidly it evolves in time, the more rapidly it oscillates in time, the bigger d by dt, the bigger the energy is. Now that's an imprecise hand-waving statement. This is a more precise statement, but the key point is, from one perspective, it's plausible to ask the question, how rapidly does it grow old? How does it evolve in time more precisely? What's d by dt of the wave function? That in some sense should be proportional to E. Again, the more precise form of that statement is viewed by viewing this equation and obtaining this result. We can ask a similar question of momentum. Now let me give the concepts first. Here's one plane wave. Surfaces of constant phase, separated by some distance lambda. Here's a plane wave of higher momentum. And the wave vector k is correspondingly bigger because the wavelength lambda is smaller, and the momentum is bigger because k is bigger, p equals h bar k. The point is that as a plausibility argument, instead of asking how does it evolve in space, what's its temporal derivative, here how rapidly it evolves, instead of asking how rapidly it evolves in time to get the energy, we can instead ask how rapidly does it evolve in space. And so you would expect, and that's what the gradient operator does, it tells you how rapidly an object evolves in space. So we want to extract momentum from the plane wave function. We want an eigenvalue equation, just like shown above. If you apply the gradient operator to this object, you may need to write this out component-wise if you need to revise your vector analysis, and when I was in your shoes I did need to, but the bottom line is that when you apply the gradient operator to this object, you differentiate with respect to t, you essentially pull out E. If you differentiate with respect to space, which is what grad is, then what you pull out is a coefficient of the vector r, in other words, essentially momentum. But there's an I on h cross, which you fix up with a minus I h cross. So the key point here is that spatial derivative essentially tells you momentum. Now deriving these expressions from the plane wave is exercise 11. These are the Schrodinger correspondence rules. Again, I emphasise we're not proving anything here. These are plausibility arguments. Whose utility, again, is ultimately derived via whether or not you get agreement with the experiment. Again, I just want to emphasise we've got our wave function. And this diagram I'll draw a few times during this course, and it will get progressively more sophisticated. We use the momentum operator. Now let me introduce a piece of notation. When you put a hat on a vector, or when you put a hat on a quantity, it means unit vector. Hats also mean operators. So hat means two things: a unit vector if it's on top of a vector, but a hat also means an operator. Unfortunately, same notation for two different objects. So the momentum operator, the energy operator. So we could put hats on the left-hand side of the boxed equation above. We use momentum operator to extract momentum from the wave function, which is total knowledge of a quantum system. We're using energy operator to extract energy. And if you have some other physical quantity A, then you'll use its corresponding operator, A. Again, we'll have more precise statements to make regarding this idea of operators in quantum mechanics in the next class. But for now, we have operators for energy and momentum via the Schrodinger correspondence rules. We've completed section 7. We're now going to use these operators to motivate the Schrodinger equation. And it's going to have two forms, and the more general form will be the time-dependent Schrodinger equation. Now let me just abbreviate that as TDSE. Section 8, time-dependent Schrodinger equation. Now, before we give the plausibility argument for motivating the Schrodinger equation, let's write down some requirements for this equation. 3 requirements. The first is that the equation be first order with respect to time. Now, this is first order in the sense of differential equations. WRT means with respect to. So first order with respect to time. Why are we going to demand that the wave function, or the wave equation, or the Schrodinger equation more precisely, be first order with respect to time? In other words, the highest order of derivative with respect to time will be first derivative. Now this is necessarily going to be a partial differential equation because psi is a function of many variables, x, y, z and t. Since it's a partial differential equation, we have partial derivative here. And the first question is, why do we demand this? That the Schrodinger equation be first order with respect to time. And the answer seems almost philosophical. I've spoken of this wave function as giving total knowledge of the quantum system. If this indeed gives total knowledge regarding the quantum system, then if I tell you the wave function at some particular time, let's say t equals t0, if I tell you what the wave function is at that particular time, that should tell you everything you need to know about the wave function. Hence, you should be able to work out what the wave function is at any point in the future. So if I tell you this initial condition, the wave function at time t equals t0, I should be able to derive, and we'll learn how to do this later, how do you propel this in the future? How do you make this wave function at this instant of time, how do you make it grow old? How do you work out its value at some time t, which is greater than or equal to t0? If this gives you total knowledge, then knowing this at t equals t0 should be enough to evolve it into the future. Now, if your differential equation, which governs how your wave function evolves in space and time, if your equation is second order with respect to time, you need to integrate twice. You need 2 initial conditions. But I'm only going to give you one, which is this. If it's first order with respect to time, you need to integrate once. You need 1 initial condition, which is precisely this. So first order equation with respect to time is consistent with the initial condition being enough to evolve the equation into the future. Just as a piece of context, suppose I have a string. Here's a string. And suppose I tell you that this is the shape of the string tied to 2 fixed points in a wall. I tell you that this is the shape of the string at time t equals t0. And suppose I was to ask you to evolve this thing into the future, to tell me what the string looks like in 1 second. The answer is you don't know. Telling you the shape of the string at time t equals 0. And now let this be height hx at t equals 0, and this is the x coordinate. If I just tell you the height of the string at time t equals 0, I haven't told you how fast it's moving. I need to tell you both the height of the string at t equals 0 and how fast it's moving. H dot, derivative with respect to time, is velocity. Yep. If I tell you 2 things, 2 initial conditions, then you can tell me what the string looks like in the future. its position, its displacement, and its velocity. The equation that describes strings is second order with respect to time. It's a D'Alembert wave equation. Yep. So the key point here is second order with respect to time, two initial conditions, and this object does not tell you enough to evolve it into the future. If this is total knowledge, this initial condition should be all you need to evolve into the future. Therefore, the Schrodinger equation should be first order with respect to time. The second of three requirements. This has to be a linear equation. And this is just the superposition principle of quantum mechanics. It needs to be a linear differential equation. Yep. If psi A is a solution and psi B is a solution, then the sum of those two, psi A plus psi B, the superposition of those two solutions must also be a solution. This demand that the time-dependent Schrodinger equation be linear is a direct embodiment of the superposition principle. Just as an aside, if you're doing quantum chaos or quantum turbulence, you actually replace the Schrodinger equation with a nonlinear form. And for example, if you have a very cold quantum gas, a so-called Bose-Einstein condensate, abbreviated BEC, and we have two world-leading Bose-Einstein condensate laboratories at Monash, cold cloud of quantum gas. When I say cold, I mean billionths of a degree above absolute zero. Cold cloud of quantum gas. Its evolution is described by a nonlinear form of the Schrodinger equation called the nonlinear Schrodinger equation, and that nonlinearity allows this thing to exhibit chaos, quantum turbulence. It's an area of active study here at Monash, but that's a story for another day. Linear equation is a second of three demands. And the third demand is that the Schrodinger equation must preserve normalization of the wave function, a term that I'll explain now. So remember the Born interpretation of quantum mechanics, which I'll revise now. The magnitude squared of the wave function is a probability density, a probability per unit volume. What do we mean by that? If I have some little box of volume dx, dy, dz, it's a scalar which I denote by dr, then this is proportional to the probability per unit, probability of finding an electron at this point r at a given instant of time t. More precisely, if we multiply a probability per unit volume by a volume, this is the probability that at time t you find the electron to be in this little box of volume dr at position r at time t. This, if you add them all up, add up every box, add up every probability, add up over all space, then this object will be 1. This is the probability of finding an electron anywhere. This is a single electron wave function. This is always the case whether I say it or not. Single electron wave function. What I'm underlining now is the probability of finding an electron somewhere. So suppose I give you the Schrodinger equation and suppose that at some instant of time, t naught, this is true. But we want this to, this is true at t naught. The Schrodinger equation can then be used to make a wave function grow old, to evolve in time. Again, we learn how to do that soon. The question is, if this is true at a given instant of time, let's say t naught, is it true at all time? This condition is called the normalization condition, and the fact that the Schrodinger equation preserves normalization in time t, is going to be a demand. So these are the demands that our Schrodinger equation must obey. So let me, with these in mind, obtain the Schrodinger equation via the Schrodinger correspondence rules. And in doing so, we're actually going to beat a path from classical mechanics, CM, to quantum mechanics. So in this context, and by the way, later in the course, we'll learn how to go backwards. Interestingly, going backwards is a lot harder than going forwards. Going from here to here can be done in 3 minutes or 5 minutes, and I'm going to do it now. Going from here to here is still an active research problem that's incompletely understood. That seems ridiculous. If you can go from here to here, you just go backwards, right? It's not that simple for reasons we'll explain in a subsequent class. But for now, we want to use the Schrodinger correspondence rules, the SCRs, to get from classical mechanics to quantum. So classical mechanics, in what sense? Well, here's a billiard ball with momentum p, and space is filled with some scalar potential v, which is a function of position and time in general. And that background scalar potential can exert a force on the particle, which, as you know, is minus the gradient of the scalar potential. What does Newton say about the energy of this particle? Well, Newton would say that the energy of this particle is kinetic plus potential. What's a kinetic energy? Well, it's half mv squared, which is the same thing as p squared on 2m, which is the same thing as p dot p on 2m. So this is a kinetic energy where p is the momentum and m is the mass. Energy is kinetic energy plus potential energy. So this is what Newton would say. What would Schrodinger say? Well, Schrodinger would say, take this equation and apply the Schrodinger correspondence rules. Replace E, the box at the top panel, replace E with I h bar d by dt. Replace E with I h bar d by dt. Yep. 1 on 2m stays where it is. Replace P, again, the box in the top panel, replace P with minus I h cross grad. So P is minus I h cross grad, dotted with itself, dot product. That's it, plus potential. So we've just taken the Newtonian result and applied the Schrodinger correspondence rules. So the question is, how do we proceed? We're about 2 steps away from the time-dependent Schrodinger equation. Now we need to be very careful. So let's take this equation and expand it. So let's be careful. Here's a mistake I made. Negative a number times negative a number is positive, and so I squared is negative 1, so this is positive 1. Negative I times negative I. You need to be careful. The negative times the negative is a positive, and the I times an I is a negative. Yep. So negative I times negative I is in fact a negative. Yep. So our equation is going to be IH cross d by dt. And I'm leaving a judicious space here. We've got 1 on 2m. There's a h bar squared. There's the negative and the negative gives a positive, but the I and the I gives a negative. Grad dot grad is grad squared. And again, please spend an hour revising your vector analysis. If grad, div, curl, divergence theorem, Stokes theorem, etc. Are not absolutely fluent in your head, because we'll use them a lot. Plus the potential. Now, I would call this an operator equation. I'd call this an operator equation because it's an equation that involves operators, right? Differential operators, such as temporal and spatial derivatives. Again, this is not a derivation. This is a piece of ad hocery that's ultimately justified via its consistency with experiment. I'm going to post-multiply, in other words, multiply on the right by the wave function. It wouldn't make any sense for me to multiply by the wave function on the left. Yeah, these are operators, so you need to be careful about order. Psi times d by dt is different to d by dt of psi. Yep. I want to post-multiply, in other words, multiply on the right-hand side by the wave function, and that converts the operator equation into a partial differential equation, and this is the time-dependent Schrodinger equation. called time dependent because time appears explicitly in this object. So this is our time dependent Schrodinger equation. And this time dependent Schrodinger equation is the second most important equation in this course. Now, given that we've motivated the Schrodinger equation, again, ultimately, if it gives us the right answers to within a given accuracy, then it's a good equation. If it doesn't, then this logic goes out the window, or this plausibility argument goes out the window. This equation works fine, provided certain effects can be ignored, provided you don't try to work with too high a precision, provided several other things I won't go into now. The point is, this describes a vast variety of quantum phenomena with acceptable accuracy. As always, experiment is the arbiter of any theory. Let's go back to our requirements. We wanted an equation that was first order with respect to time. This is first order with respect to time. We wanted a linear equation. This is a linear differential equation. If you had terms that looked like the magnitude of psi squared, that would make a nonlinear equation. And I just can't help myself for a second. If you want to write down the nonlinear Schrodinger equation, it has this form. There's another term in here in the red brackets, which is a constant, a coupling constant g, a scalar, times the magnitude of psi squared. This is the nonlinear Schrodinger equation that describes quantum turbulence in Bose-Einstein condensate and other nonlinear quantum systems. That spoils the linearity of the equation. Superposition principle doesn't work anymore. This is a linear equation. It obeys a condition 2. In the notes, I ask you to explore this explicitly, or I do explore this explicitly, by showing that if psi A solves this equation and psi B solves this equation, then the sum of the two solves this equation. And this is explained in detail in the notes. Please work through that. The third condition, that it preserves the normalization of the wave function, is left as an exercise, exercise 12. And that's actually quite a challenging exercise, but it's also fun. And it also revises and uses many results from vector analysis. I want to close this section with an apology, and it's as follows. This energy operator which this energy operator is IH cross d by dt. That energy operator is also the right-hand side because they're equal. So we could speak of this as the energy operator. We could speak of this as the energy operator. We give this a name that's used in this course, which is Hamiltonian. The apology is that for this course, we just use these two terms interchangeably. The reason I'm apologetic about it is because it's called a Hamiltonian, not just to introduce some pointless extra term, which means the same thing as this, but that's what we'll do in this course. But there's something very, very deep here. There's a so-called Hamiltonian formulation. This is a term after William Hamilton, the famous mathematician. There's a Hamiltonian formulation of classical mechanics. There's a corresponding Hamiltonian formulation of quantum mechanics, which is essential for much more advanced studies on quantum physics and classical physics. But we don't need this for this particular course, beautiful and interesting and powerful though it is. So for this course, I just use the term Hamiltonian to mean the energy operator, the left, or more typically the right-hand side of this equation. But if you're interested in looking deeper, pick up any decent classical mechanics text. And the best one is by Herbert Goldstein. And it's called, and sorry, the latest edition is by Goldstein, Poole and Safko. Now this is a book on classical mechanics, which has a beautiful discussion of Hamiltonian classical mechanics. And even though this is a book on classical mechanics, it also tells you how Hamiltonian methods are used to make a transition, or can be used to make a transition from classical to quantum theory. I should also point out that those of you doing PHS3131 will learn about Hamiltonian methods from Csaba Balázs's lectures in that course. All good stuff, and I'm sorry I'm not going to talk about it anymore. All right. Section 9, the time-independent Schrodinger equation, which I'll abbreviate as TISE, time-independent Schrodinger equation. Now, if the Schrodinger equation is the second most important equation in this course, in other words, the one that we spend the second greatest amount of time solving, the most important equation is going to be this one, a time-independent form of the Schrodinger equation. Now, I want to begin with an analogy. Suppose that you had some fountain or some hose, and that hose was sending forth water, and that this hose sending forth water is steady state flow. So I'm putting quantum mechanics to one side for a second and talking about steady state flow. What do I mean by steady state flow? Well, if I wanted to describe the water travelling through space, I could describe it or partially describe it by its velocity at each point in space, at each instant of time. This would be, if I wanted to totally describe it, I would also give the density of the classical fluid at each point in space, at each instant of time. This is a density in the context of classical fluid flow. Steady state flow loosely would mean if you took a picture of this water stream, at any time it would look the same as at any other time. More precisely, these two objects, v and ρ, velocity is a function of position and density is a function of position. In general, they're dependent on time, but if they're independent of time, and think of the I for independent here, if they're independent of time, you have steady state flow. This object, or this photograph of the flowing water, looks the same at each instant of time. That's a special case of arbitrary flow where you have full time dependence. Similarly, the time-dependent Schrodinger equation has a special case for the quantum mechanical analogue of steady state flow, and that special case is going to be called the time-independent Schrodinger equation, which we want to derive now, and which, as I said, we'll spend more time solving this equation than any other in this course. So I want to return to our friend, equation 15. And this was our superposition of plane waves. Yep. We want to make up an arbitrary wave function psi. How do we do it? We take our friend, the plane wave vector k, position r, angular frequency omega. That's one plane wave, which is labelled by its particular wave vector k. I now weight it with some weighting coefficient, the momentum space representation of the wave function, psi tilde of k, that's a tilde. I make that weighting coefficient infinitesimal. I add them all up. I put in a pointless constant, which is due to convention, 1 over 2 pi to the 3 on 2. This is a superposition of plane waves. This is how we make an arbitrary wave function. Now, with a view to obtaining the time-independent Schrodinger equation, I want to consider a special case of this. So what I'm about to do involves a loss of generality. As an analogy, if we were talking about the light in this room, the general case of light filling this room would be white light filling this room. A special case would be light of a particular wavelength filling this room. Imagine that this room was just filled with red light. Imagine this room was just filled with light of a particular energy. Imagine that this wave function was built up of plane waves, all of which had one particular energy. Now remember that E equals h bar omega. So if we're just adding up plane waves of a particular energy, this quantum mechanical equivalent of light waves of a particular frequency or colour, then they're all going to have the same. Every plane wave in this sum, in this superposition, will have the same angular frequency omega. So this object here, which in general depends on k and hence must be inside the integral, this omega, by assumption, and this involves loss of generality, is going to be independent of k, and therefore e to the minus I omega t can be pulled out the front of the integral. So we've made a special case where our e to the minus I omega t, and I'm about to rub this off in a second, can be pulled outside the front of the integral. What's left? Well, we've got 1 on 2 pi to the 3 on 2. We've got a triple integral, psi tilde of k, etc. K dot r, decay, and that's it. Now omega is the same as E on H cross. As I've said many times, arbitrary integrals can't be done, so therefore they're easy because you can't do them. If I just look at this and say, well, what is it? The answer is you can't go any further because it's arbitrary. Now, having said that, k is a dummy variable. It's integrated over, it doesn't exist. This thing is just a function of r. K is a dummy variable because it's integrated over, it's gone, it doesn't exist. R, however, is a free variable. So this object here is a function of r, which I'm going to denote by a lowercase psi. So this time-dependent wave function, for this special case, that we're adding up plane waves, all of which have a particular energy. And since this is a special case with all plane waves having a particular energy, let me put a capital E subscript on this thing. That's going to equal this object here, which is, by the way, independent of time. And compare the fact that these things are independent of time, compare the fact that this picture is independent of time, multiplied by this harmonic time dependence, e to the minus I et on h cross. So this is a factorization into a product of a function of space and a function of time, of a monoenergetic wave function. There's only one energy here. This is monoenergetic wave function. Again, a special case. This is given a name. It's called the spatial wave function. And again, this idea of uppercase psi for an arbitrary time-dependent wave function and a lowercase psi for a so-called spatial wave function is terminology we'll use very often. A logical next question to ask is, what form does the time-independent Schrodinger equation have or take when you have a time-independent scenario corresponding to a monochromatic beam, a monochromatic wave function, a wave function describing plane waves, all of which have the same energy? By the way, in such a scenario, energy is precisely defined. And your understanding of this statement I've just made will deepen through application throughout the course. But for now, we want to ask the question, what is the time-independent form of the Schrodinger equation? So we're working towards equation 47. So to begin with, I'm just going to write out the time-dependent Schrodinger equation. IH cross d by dt acts on the wave function. This is the boxed equation in the middle panel on my right. IH cross d by dt acts on the wave function, which is little psi of r from the middle panel. Little psi of r times e to the minus iet on h cross. And this is all equal to, again, middle of the top panel. So the top of the middle panel on the right, minus h bar squared on 2m, etc. Our potential V, and that acts on the wave function, which we're writing in our special form, spatial wave function times harmonic time development. Now, before I continue, I want to make an approximation. I want to describe a time-independent scenario. I don't want to let my potential depend on time. I want a time-independent potential. For example, you might have the potential field which surrounds the nucleus, which is holding an electron to a hydrogen atom. If this potential is time independent, then you have a time independent potential. The T can be crossed off. There's loss of generality here. I'm explicitly assuming that the potential is independent of time. Next thing, I want to do the d by dt. When we do d by dt, we're going to pull out a factor of minus I e on h cross. In other words, we pull out the thing that's multiplying the t. Yep. What's multiplying the t? It's minus I e on h cross. So when we do d by dt, we just replace it with minus I e on h cross. Minus I e on h cross. Now we set up the Schrodinger correspondence rule so that we should get an e out the front. Minus I squared is 1. And the h bar and h bar cancels. Yep. So we're left with an e out the front. That's no surprise because our Schrodinger correspondence rules were designed to make that happen. Next thing, the only place that t appears is in this exponent that I'm underlining. That's the only place that t appears now. So we can just cancel it. And what we're left with is the most solved equation in this course, namely the time independent Schrodinger equation. And I'll write out the right-hand side out first. So minus h bar squared on twice the mass of the particle, Laplacian, time independent potential by assumption, spatial wave function, and that equals the energy, which is a scalar and well defined for this object, times the spatial wave function once again. So this is the time independent Schrodinger equation, so called because it's independent of time. And again, this is, I said it too many times, we're going to use that a lot. It's important. It's equation 47. I've mentioned the idea of eigenvalues before and eigenvalue equations. This is an eigenvalue equation. If I was to call this some linear operator, let me call it an L. This is the linear differential operator. This has the form of an eigenvalue equation because the linear differential operator, L hat, acts on the eigenfunction, which is a spatial wave function corresponding to a particular energy, to give the eigenvalue, which is the energy, times the wave function back again. So I just want to note that this has the form of an eigenvalue equation. I want to close by talking about one further thing, which is the boundary conditions for the wave function. So boundary conditions for the wave function. Unless I annoy you by doing this too much, this is another piece of ad hocery, which I can't, and neither can anyone else, justify from first principles, except by saying it works for experiment. So boundary conditions, in the sense of mathematical differential equations, boundary conditions for the wave function psi. So this is going to be a set of 3 conditions that we're going to demand be true. So condition 1, condition 2, and condition 3. So condition 1, in loose terms, demands that this wave function be well behaved. More precisely, that it be continuous and single valued. It's got to be a continuous function of position and time, and it's got to be single valued. In other words, at any particular point in space, at any instant of time, this should have one complex number associated with it. Continuous, single valued function of time. Second condition, a bound wave function. Think that the reading at the very end of the very last lecture, a bound wave function is essentially one that vanishes at infinity. It corresponds to some localized quantum system. Psi is essentially 0 outside some volume. More precisely, psi must tend to 0 sufficiently rapidly to infinity. Bound wave functions must be square integrable What do I mean when I say that a bound wave function must be square integrable? I mean that the integral of the magnitude squared over all space, I've rubbed it off, the integral of the magnitude squared over all space must be finite. Yep, so this object cannot diverge. This is what I mean by bound wave functions must be square integrable. And the third and final condition, which I'll write right out, again it's a demand that at any given time the spatial derivatives of psi, in other words grad psi, must be continuous everywhere except possibly at points where there's an infinite discontinuity in the potential. We'll draw on these from time to time during the course. For now, these are just demands. But as a challenge to you, I ask you the question, what the hell do these things mean physically? Because I'm not going to tell you, because you're smart and you can work it out for yourselves. What does these three conditions mean physically? Thank you. I'll see you next time.